I mean, it as complicated as it might, it might get. If you keep reminding yourself, for the basis of all this stuff is the theory, and that's what it is. It's a theory, right? So this is not fact. This is, like basically a set of assumptions that we're using to try to understand people's responses, right? So keep that in mind. This is not, this is not hard facts, right? We're just trying to do the best we can with the information we have. So we are assuming that everyone, whatever you're measuring, right? Everyone has some real value on that. So think about it, something more concrete. Everyone has a height, right? And depending on a number of things, you can get some variability in measuring people's height. You with me so far? So it could be, if you know this or not, but some days you're a little taller, a little shorter than other days, just from basic things like how you slept, how you stand, the spaces, between like your, what do they call them, your discs and your spine, there's different, you'll get some variability. So in reality, everyone has sort of an actual, like, concrete height. But as we go to measure that, even from day to day, you're going to get some variability, some error in there. So the whole thing about classical test theory is, let's try to figure out what the error is relative to the true score. And if we could figure out sort of where the error is coming from, or what types of errors are going on, we can get closer at trying to capture the person's sort of true score. The problem is, in general, is that we don't typically apply that to a single person, meaning that I'm not trying to predict exactly someone's true score. You can using this sort of methodology, but usually it's, you have a bunch of people who responded to a scale. Let's figure out what portion of the variability is due to sort of noise, and then we can capture what portion of that variability is due to people's just individual differences on their true score. So that's why most everything is written about, like in terms of variances. There is some variance that's really due to individual differences, and then there's also variability that's due to just measurement error. And we're trying to separate those two out. Again, you can try to apply this to predicting people's individual scores, but we're using this knowledge to then try to figure out how well the scale is actually doing, how good it's doing at trying to capture people's, whatever it is. In this case, it could be height. It could be anything. It could be, anxiety. It could be intelligence, whatever you want. So this is all just looking at how we can break the variability down and use it as a way of looking at sort of reliability. How consistent is that true variability being captured from in this case, one time to the next? That's why it's test-retest reliability. So the thing to keep in mind is, classical test theory is driven by this idea of trying to separate out variability that's due to error and variability that's due to real individual differences between people based on their true scores. That's like the gist of every part of this. It's just, how do we sort of separate them out? How do we figure out what's due to error and what's, what's noise and what's real variability? And we have to go through these sort of tricks like test-retest. If we give someone a test, if we just give one test, doesn't matter how many items there are on the test. So we sum them up and we get a score. And people vary on that score. We sort of saw this a little bit with when you took the CESD. Your scores probably varied a little bit. The person you were measuring probably varied a little bit. But if you just have one of those, you really can't tell anything about that. So there's no real way to tell what is a person's sort of true depression level versus noise with just one measure. So we have to give it again, see how consistent it is. And any part that's consistent, then we're assuming, this is part of the theory, that it's due to their true level of depression. And any part that is inconsistent, then it's just sort of random noise. That random noise could be due to measurement error, but it could also be due to just fluctuations in people's, there's some certain portion of your response to this scale that may not be due to a trait, but maybe due to some kind of state factors. You just happen to be having a bad day that day, so you score a little worse. You're having a good day, you score a little better. So there are other things that contribute to it, but it all gets sort of lumped into to noise, to measurement error, and we're assuming the rest of it that's consistent is the true score part. And that was a That wasn't everything about classical test theory, but it does sort of, I think, bring us back to the point where we are now in terms of review. Okay, good. Making sense is good. I don't always do that. So when I do make sense, it's good. It's awesome. So the problem with the terms reliability and validity, which we're going to talk about more so in the next section on validity, is that the term gets used to apply to so many different things. So when you're talking about the reliability of an experiment, you're usually talking about things like control over the experiments and internal validity. Okay, so this is where things start to get confusing. People confuse reliability and validity all the time because there's so much sort of overlap and there's a lot of gray area between what is validity and what's reliability. And in truth is, validity relies on reliability and it's all kinds of stuff. But typically reliability refers to the measure that you're using. So even in an experiment, if you're using something, like if I want to use the CESD as an outcome measure in an experiment, I want to show that it's actually reliable. Now I can do that by just citing literature saying, look, people have used this scale, they've done test-retest reliabilities and other kinds of reliability tests, so I'm just going to trust that it's reliable. Or I might within my own sample, have them do a test-retest so I can show that with the sample that I'm using, it's reliable. But that's separate than sort of if I'm doing some kind of manipulation, like if I'm randomly selecting people, half of them are going to go to some kind of treatment for depression, the other half's going to not do that, like some kind of waitlist control thing. You're talking about sort of the validity of the experiment, which is separate from the reliability of the measure. Right, but you can see no matter how good a job I do in manipulating the treatment, if my measure isn't reliable and my measure isn't valid, it's not going to matter. It's going to dramatically impact the experiment. So I can have an internally valid experiment, but with a poor, unreliable measure, it's going to dramatically hurt my chances of really finding anything conclusive. So they're all sort of intermingled and tangled up together. That's why people oftentimes will get a little bit confused about what is validity, what is reliability, and how, what's the difference between those things. So, okay, it's an excellent question. Right here, actually it isn't right here. It's actually on the next page. Nope. It's back a ways. We talked about this idea that one of the things that's interesting is for it to be error, is that error and here that the expected value of x is the true score. It's like the long run error. The error is simply just a difference between what they scored and their true score. It's just some variability. Think about like prediction, right? This is the residual. And one of the things that we assume, I thought it was on this page, maybe it's not. I thought there was some place where it says that, here, we assume that error, these are all assumptions. So anytime you see assume, this is something that we're assuming in order to sort of make this stuff work. It doesn't mean that it always applies or that it always works. But we are assuming that whatever the errors are, they are unrelated to the true score. So it has something to do with, it's just random measurement variability. It's something that has nothing to do with the person's true score, which gets a little fishy. Like I just said a second ago that, well, sometimes, if I'm taking a depression inventory, sometimes I may be having a good day and I might score a little high, score a little lower. Other days I might be having a bad day, score a little higher. So there's some variability that's due to me, that's internal. And that portion really isn't necessarily unrelated to true score, but we're still going to treat it as if it's unrelated. We're going to assume that it is, because we're not going to be able to separate that out from variability that's due to the instrument, to the measurement scale itself. So I'm trying to think of diagram, way to draw this out, how they're unrelated. So one way to think about this is, and it's not, I don't know if it's here somewhere. I mean, this is basically, with and without. It fattens up the measure around the true score. But, I didn't mean something diagram. There is some place. One of the things to keep in mind is that we're assuming that the error that's attaching itself here I know it says it's normally distributed, it's uncorrelated, has a mean of 0. We're also assuming that it's random. So one of the things that is interesting, anytime you hear somebody say a random variable, it's a random variable. So if something is random, or varies randomly, it shouldn't share any variation in anything else that's random. Because the very nature of the word random means that it has no pattern. It shouldn't share anything. So if I have two random variables that they're supposed to be independent of one another, which is the true score is random across people, and error is random across people as well. They're both random and they're supposed to be independent. Well, part of the reason why they're supposed to be independent is E is supposed to be impacting the measure of true score in a random way. So for some people it increases the score, for some people it decreases, for some people it makes no change, right? But the way it acts upon the true score is supposed to be random, normally distributed, and is around 0, meaning that it's affecting people plus or minus, about the same amount across a whole bunch of people. So the sum of all the errors will be about 0. But the main thing is it's supposed to be uncorrelated with the true score, because if it's correlated with the true score, then it's not really error. It's not really random. It actually is related to true score, which means there's variability that's affecting the person's score that is outside of that particular measure. I'll give you an example that hopefully will make it clearer, but it might confuse you more. So let's see. One of the things you've heard of comorbid disorders, right? You heard that term before, comorbid? Okay. Depression. Does anybody know what depression is highly comorbid with? Anxiety. It's really, really difficult to even separate out anxiety from depression when trying to measure it. So one of the things that will happen when you measure depression that'll make E not so independent, or not, that'll actually make these correlate, is that as I'm trying to target depression, anxiety will actually impact the measure of depression, making people's scores sort of move around, and it's going to be treated as error, but it's also going to make the error correlate to the true score a little bit because it's being impacted by another measure. So there's something else that's acting upon a person's score that isn't truly random. It's not just a random noise that's being added to the true score. There's actually something else really going on there, and that's because it's related to the thing you're trying to measure, depression, but we're trying to treat it as something separate. We're not including it in the measure. So oftentimes people will measure depression and anxiety at the same time and try to separate out the different scores and see where the two things are unrelated to get measures that are independent, to get like a depression measure that's independent of anxiety. And there's been attempts to do this. Like there's a scale called the Beck Depression Inventory, and it has a companion measure called the Beck Anxiety Inventory. And the Beck Anxiety Inventory was specifically designed to try to measure anxiety that isn't correlated to depression, that's sort of separate, independent from depression, or at least to reduce the amount of correlation between them. So, think about, you got to think about this is across people, right? So you have people's true scores that are sort of varying across here. What the measurement error does is to sort of add more variability to the score, add more noise. So we're really trying to capture what's really happening here by identifying what is sort of the noisy aspect of the measure, and sort of pull that apart to see how well the thing does at trying to capture the true score. Again, not for an individual, but across samples or groups of people, and looking at the sort of variability due to error and variability due to the true score. All right, we gotta move along. We're gonna run out of time. Okay, so we looked at this idea of you give the same test twice, and regardless of how much of this you really pick up on, this is it, as a sort of mathematical explanation. But the idea is that if I give you a depression inventory today, and you take it again in 3 days or in a week or whatever it is, the amount of correlation between those two administrations, the part that's consistent across the two administrations, right? So if you were high on the first administration, you're high on the second. If you're low on the first, low on the second, that degree of consistency, we are assuming, based on the classical test theory, that that's being driven by the true score. The parts that are inconsistent, meaning that that you weren't perfectly the same from beginning from the first administration to the second, there was a little bit of variability in there. we're assuming that any inconsistent parts between the first and second administration is due to measurement error. So we can actually then use that idea that there's consistent scoring from pre to post that's being driven by the true score. So the more of that, the more that a measure stays consistent from pre to post, the better it is at capturing that true score. It's more reliable. Which is a separate question than asking, did we actually measure the thing we were trying to measure? That's validity. Okay? So whatever it is we're trying to measure, it doesn't, in terms of reliability, if you're measuring the right thing, the correct thing, doesn't really play in there. All reliability cares about is whatever it is you're measuring, did it do so in a consistent way? The more consistent it is, the higher the reliability. All right. With that in mind, so test-retest is sort of easy. It's got the exact same test twice. But what are some problems there? What are some issues with that? So the sources of error, like where we think error might be coming from, is things like random fluctuations in performance. So think about this as being IQ or achievement testing or something like that. Depending on the day, you got either more or less sleep, you are more or less caffeinated, or whatever it is that sort of helps you sort of attend to things. You could do better or worse even on the same IQ measure. So there's going to be some fluctuations in performance just based on time. Not everyone's going to score exactly the same every single time they take a test. Other things like uncontrolled testing conditions, things that have changed from pre to post. So when you took the depression inventory that I gave you as part of your homework, you took it, did you take it in the exact same place at the same time of the day? There were probably variations. You may have taken it, in different places, and the person you gave it to may have taken it different places. So just the place, there are more or less distractions. There are sudden noises or chronic noise that could be in one setting but not in the other. They have extreme changes in weather. That seems kind of out there. But, you could think of anything that would change between testing conditions. Like for instance, imagine you take in an achievement test. You want to do test-retest reliability, and you're doing it someplace back east, and they take it one day, and the next day, there's a freak, snowstorm. Everyone's sort of coming in the snow. They had to get up extra early just to sort of, get into class and take the thing. So those types of changes in the testing conditions can actually dramatically change how they respond. There are lots of other things like, internal factors, like I mentioned before. Someone's sick one day and not the other. There's fatigue, emotional strain, worry. You can be more distracted because of stuff going on in your life. Recent experiences, you actually may do better on an IQ test because you took an IQ test. In between, you then started to look up things. You actually like, I didn't know that question, so I'm gonna go look up that topic and see if I can learn more about that. And then you may do better on the second administration, and it actually jacks up the reliability because you actually change quite a lot based on just doing things differently in between. This recent experience is an issue called local history. Things that happen in between administrations can actually impact the reliability. So with all that being said, sources of error, one of the things that this is good for is you can really only use it to evaluate constant or at least consistent traits. Things like intelligence, personality. Like you wouldn't want to have a test of like hunger or something that we try to test reliability, across multiple days or something like that, because, your hunger is affected by such proximal things, things that happen in that day, that it's going to impact things a lot. It's not very consistent. So it's not appropriate for qualities that change rapidly over time, like mood or hunger. Even though we have tried to identify ways of doing things like mood, they tend to be more difficult to do. Like there are, even for anxiety, there are trait measures of anxiety and there are state measures of anxiety. The state ones tend to have a lot lower reliability. So a big problem with this is something called carryover effects. So is the reason why people score consistently because the measure is reliable, or because they remember the test from the time before and they just respond the same? Oh, I remember I scored this on the last time and I was going to mock the same answer. Right, so carryover is a problem in lots of things. Anytime you have someone doing something twice, like a test, retest, or pre-test, post-test kind of study, carryover is always going to be an issue. And a really good example of carryover effects outside of sort of research is if you've ever gone like wine tasting or any kind of tastings of any sort, whether it's like whiskey tastings or tequila, whatever, any kind of tastings, you would typically, they give you like food, crackers, bread, stuff like that in between, and water in between the tastings to try to reduce the amount that the first thing you taste carries over and affects your tasting of the second thing. So they're trying to sort of cleanse your palate in between to avoid the taste of one carrying over to the other. So that basic idea there is this idea of trying to combat sort of carryover effects. So anytime you do something to somebody, measure them for some reason, even give them an IQ test, when they come back and you take the IQ test again, it's likely they'll do better simply because they saw the test before. Okay, so that change, these carryover effects, can impact the reliability. You can actually make some tests more reliable because people remember what they put. But if it actually means that people change the way they respond, it actually can lower reliability if it changes some people more than others. Right? So it's only a problem when the effects are sort of random, meaning that if the carryover effect is sort of consistent, so if everyone is here, right? Let's say this is time 1 and everyone's here, and this is like, you know, the highest person scoring, next person, everyone's sort of scoring at different rates. If everyone goes up the same, they're still going to be perfectly related or highly correlated, and their reliability is going to be high. If the carryover affects everyone the same, it doesn't really matter. It's when it affects people in a random way where it raises some, lowers others, that actually will start to impact the reliability. Right, so, you know, if everyone goes up 5 points, you still have the same variability. People are in the same order. You're going to have the same correlation. It doesn't really make a difference if everyone sort of moves up in the same amount. It's only when it starts to impact people differentially and it has a sort of a random impact on people's scoring that carryover can be a problem when testing reliability. All right. All right. Get to more fun stuff. One type of carryover effect is called practice effects. You know, just by simply having done something once, you make it better at it again the second time. So some skills improve with practice. So anything that requires manual dexterity or ingenuity or creativity, people are going to likely do better the second time. So practice effects may not benefit everyone in the same way, so that can actually hurt the reliability. Carryover and practice effects. It's really weird. It actually should be it doesn't matter. Carryover and practice affects more of a problem with short inter-test intervals. This quote, you know, ITI, inter-test interval. So what that means is that if you're giving people a test that are really short, between like 1 day apart, a couple of days apart, practice and carryover are going to be more likely because they can remember what they did. The test is sort of still in their memory. It can affect the way that they respond to the second. As ITIs get longer, the problems with practice and carryover stop being an issue, but other issues start to be a problem, like developmental change, maturation, exposure to historical events, things like that. So some examples of that. If I am trying to develop a math test, a math ability test to be given out in like 9th, 10th, 11th, and 12th grades, the changes in ability can be due to increases in math ability, right? But there's going to be a lot of changes that are just caused by developmental change. You know, kids getting more mature, approaching things differently, study habits change. There's developmental changes that can actually make the test seem less reliable because they've changed a lot from one year to the next. So longer ITIs now start to become less reliable because people just aren't the same anymore. They've changed throughout that period. So things like maturation, even exposure to historical events. If you were, I'm trying to think of a good example here. if you were trying to develop a scale on people's, attitudes towards Muslims or people from the Middle East or something like that, and you give them a pre-test that was prior to 9/11 and a post-test that was post 9/11, you're going to find that it's not going to be super reliable, because that historical event would have changed people's opinions and their feelings and thoughts and all kinds of stuff because of that historical event. So it's going to dramatically, ruin the reliability. So as a weird side note, because that's the thing that came to my brain. So my birthday is 9/11. So every year now I feel like I don't want to celebrate, because it's always like a reminder of that day. But which I guess is how some people feel about Pearl Harbor Day way back in the day. But anyway, so whenever people talk about 9/11, I'm always like, oh, don't remind me. I'm trying to think of something to be related to now. So think about if you were trying to, let's see. Let's say you were trying to develop a scale to measure students' opinions about online learning, right? Taking online courses and all that kind of stuff. It's very likely 4 or 5 months ago that you may have found people's opinions, varied or whatever. They may not have had very solid opinions about online courses and online learning, but because of the pandemic and lockdown, people are now experiencing a lot more of the online learning stuff. They may have dramatically changed their opinions, and that would then dramatically change the reliability of the scale. It'd be hard to sort of show that the scale is reliable because of the historical events that have changed people's opinions they're having in between the two test administrations. All right. Okay. So that sort of wraps up test-retest. Another issue with test-retest, right, is that, not everyone wants to, because of the practice effects on those other things, you don't necessarily want to give someone the same test twice. And have that repeated. It seems like a weird thing to have to include, when really all I want to do is just measure the changes at post-test or something. So one way around trying to avoid all the carryover and practice and all this stuff is, well, why don't we just use 2 different tests? This is called the parallel forms reliability, and this goes back to the idea of domain sampling theory. So if I have a bunch of items that all are part of some domain, again, let's pick on depression, a bunch of depression items, right? So instead of developing just one depression inventory, I could randomly select items from the domain and create 2 separate but parallel, called randomly parallel, versions of the test. Because they're randomly chosen from the population, the 2 samples of items that create these 2 different tests should be randomly parallel and related to one another, and still reflect the true score in the same way, or at least to the same degree. Okay, so how would you do this? Develop a large pool of items of sort of varying difficulty. We'll talk about that later. Choose equal distributions of difficult and easy items to reduce sort of multiple forms. Give both forms close in time. Again, a short inter-test interval, and then calculate R for the 2 administrations. And this would be similar to a test-retest, but instead of the same test twice, they're 2 parallel tests. You're going to be giving one before, one after, and seeing how much they relate to each other. That'll give you an idea of how reliably those tests are measuring the true score over time. Okay, and this actually gets at this idea of item sampling error. So if you think about domain sampling, one of the things that can contribute to measurement error is the idea that the specific set of items that were selected from that particular domain are going to have their own set of sort of issues, set of variability and measurement error built into them. So the items that get sampled can actually contribute to the measurement error of the entire scale. So to address that, you can just sort of use different versions that have different sampling errors, different issues that are inherent in the items, and see if it still captures a high degree of the true score when comparing the 2 parallel forms to each other. So this is the same process really of doing test-retest. It's just you're doing test version 1 at pre, test version 2 at post, correlating them to see if they're related. And if they're truly randomly selected from the domain, they both should be equally good at, and actually, I mean, it's not just random, it's random with the idea that you're trying to at least mix up the difficult and easy items so that they're about the same in both of the tests. So you don't have one super difficult test and one super easy test, because that would be, they wouldn't be very reliable that way. And then look at how much they relate to each other as sort of pre-post measures, even though they're two different scales. And the process would be about the same. You know, use pre-post and then correlate them, and that's your reliability. There's also known as sort of alternate forms or equivalent forms reliability. You can give the forms at different times, and this also adds in sort of time and item sampling. You can give them both at the same time to see if you just want to see if the two forms are reliably measuring the same, the same thing. One of the most rigorous assessments of reliability, because it's pretty tough to actually get a highly reliable value, like a high correlation between them, because they're two different measures using different items. So it's sort of tough to do, and it requires a lot of pre-planning. So this is done to a certain degree by like ETS and stuff whenever you do the computer versions or even the paper ones, because everyone's taking a different version of the SAT or GRE or LSATs or MCATs, but they're able to sort of put everyone on the same comparable scale because they did a lot of work on the front to make sure that all they understand the difficulties of the items and are able to give everyone a test that is more or less randomly parallel to each other. So as it says, infrequently used in practice because it's too expensive to develop multiple tests to use unless you're ETS and you get the people that are paying you to take your tests to test out the items for you for free, which is what they do. Which is why, like on the GRE, there's 3 sections, but you end up taking 4 sections because one of those sections is the experimental section where they are able to get all the item statistics they need to then know how to then create alternate forms for future tests. Anyway, questions? You guys, I keep saying guys, you gals, you all are awfully quiet. So hopefully this is all making sense. If you look at this and, don't panic or anything, it's the same idea, except before we had, x1 and x2. This is just x and then x prime being just another version of x. So these are 2 different versions of the same scale, parallel forms. The idea of the correlation between the 2 of them is reliability because the covariance between them divided by their variances equals the variance of the true score over the variance of the scale, which gives you an idea of how much that scale matches the true score. And again, we're assuming because they're parallel that the 2 standard deviations are going to be roughly equal to each other. So whatever this is, when you multiply them, it's essentially just the variance of that scale is going to be a replacement for this. Is it going to be exactly the same? No, but it's going to be close, because if these 2 are randomly parallel, they should have roughly the same standard deviation. It's not going to be exactly the same, but roughly the same. So by squaring either one of them should give you an idea what the variance would be. And so we can get the reliability of x by simply comparing that to a parallel form of x, and that'll give us an idea of how reliably or consistently those measures are measuring the true score in that sample of respondents. It's all quiet. Mm-hmm. Sure. So yeah, one of the things that drives people crazy about stats, and myself included, is that they'll use roughly similar letters to mean different things. Like here I have an E, but I also have an E there, and they mean 2 different things. So this E is referring to expectation, of the expected value. The idea is if you have two different parallel scales, this one's, is X. Let's say this is the CESD. This is the CESD2, which doesn't exist, I don't think. But let's say this is just a different form of the CESD with different questions, but is supposed to be randomly parallel to the original CESD depression inventory, right? The expected value, meaning in the long run, if people were to take this sort of multiple times, the sort of average of this one should equal to the average, the expected value of this one, or they're expected to be equal. Because they're parallel, we're expecting them to be roughly equal to each other. So far, so good. Which means that the error variance for one, the amount of error that we get in parallel version 1, CESD1, should be roughly the same as the error we find here. We have no reason to believe that this one would have more error than this one. They're made to be randomly parallel, so we expect their errors to be roughly the same. So whatever that variance is, we're expecting the error variance to be roughly the same as one another. So when we go to look at this, the correlation, this is rho. This is just a population version of R. So the rho, so it's like therefore, the correlation between the two parallel forms is a way of measuring the correlation, the reliability between the form, and like CESD1, X, and the true score. So whatever is consistent about these two, the reason why people are responding consistently across these two parallel forms is because of their true score is what is consistent. This is part of the assumption of classical test theory. They're saying the reason for the reliability, the reason for consistent scoring across pre and post test, like test-retest reliability, or across parallel forms, because if they're both trying to capture the same true score, it's the true score that's really driving people's responses to both of those forms. Therefore, the correlation between any one of those forms, the correlation between the two forms is really a measure of the reliability between either of the forms and the true score. So one way of thinking about that is, so I have some true score. This is my true depression score, right? How depressed I am. And I take the CESD, all right, I'll say this is like version 1. I take that. And then I take the CESD version 2. They have they're different items, different questions, but they were designed to have an equal number of sort of easy and difficult questions or pulled from the same domain. They're designed to be randomly parallel to measure the same thing. They're both measuring depression. If people take these two scores, like let's just take the mean. So if I take this and I score whatever it is, whatever my score is on this, and I score on the second version, whatever is making my score consistent between version 1 and version 2, the classical test theory assumes that what's making my score consistent is my true depression score. How depressed I really am is what's driving it. Right, so I have some true level of depression that drives my responding here. I have some true level of depression that drives my responding there. So if I was to covary, like the version 1 and version 2 of these scores across multiple people, if this equals some some high number, like I don't know, like 0.8, where you got 80%, there's a high covariance. Let's stick to correlation. A bit easier to think about. If there's a high correlation between version 1 and version 2, like 0.8, it means roughly 80% of the variation between version 1 and version 2 is staying consistent. Well, why is it consistent? Because it's being driven by everyone's true score. Right? It's people's true level of depression that's actually driving their responses and keeping it consistent, which is what this is saying. Right? That the correlation between the two parallel forms, right, that covariance between the two forms, that this really equals the reliability between one of the forms and the true score, because it's the true score that's sort of driving those consistent responses across the forms or across the times in a test-retest. That make sense? Yeah. All right. Sometimes pictures help. Mm-hmm. So here's I've been doing a lot of thinking. I'm trying to like look up what other people are doing this time. And I was going to do this thing. I was like, oh, there's 5 of you. We can totally do a thing where everyone's together and I can watch you take a test. I'm just like, I'm not going to do it. So the test is going to be available for, I think I made it. So there's like 2 days. So I think starting on Thursday morning to Friday evening, you can start at any point. And then you have like 2 hours to complete it on your own. That being said, there's essentially any of the notes, anything you have, it's all good to use. Just don't use friends. Don't use. Don't have other people take it for you. But it's sort of open because it's online. There's no way for me to regulate any of that stuff. So in terms of the stuff we talk about in here, like this is not going to be an equation that you're going to be tested on or shown to do, but there are some like go back a second here. Did I pass it? Nope. Like here, when it's asking about this idea of unbiased reliability, this is more theoretical, likely not going to give you multiple reliabilities to then average. But there is stuff we're going to talk about, like if I give you 2 measures of the same thing, you may have to run a correlation to sort of see what the reliability is for test-retest between parallel forms. We're going to get to Chromebox alpha shortly here. You're required to sort of solve for Chromebox alpha. There are other ones, the Spearman-Brown formula, like the equations we get to later on. I'll make a note of the ones that you sort of will be tested on as we sort of go through it. Okay. I wiped off with my fingers, now my fingertips are pink. All right. So speaking of the test too, the reason why I decided on 2 hours, what I was going to do, because if I was to give this test in a regular class, like if I was teaching this in a regular semester, the class used like an hour and 15 minutes, and I was going to do it for that time. The test is only like, I think 30 questions, not super long. The 25 of them are multiple choice, and there's like 5 short answer questions. The reason why I gave you more time is one, because of the pandemic and people's work schedules and life schedule, I want to make sure that there's plenty of time for you to do it. But also because of the last short answer questions, there are some that are equation oriented. And instead of trying to figure out how to write the equations out on CCLE in their sort of testing forms or whatever, I figured you can write it out on paper, take a picture, or save it as a PDF or whatever you want, and then upload those. So that will take some extra time to do that, take a picture, upload, so there's more time for you to do those things if you need to do it. Which is why I decided sort of to do 2 hours, which I think should be plenty of time to do. I don't know. We'll see how it goes. If everyone does horribly, we may have to rethink it. But if I'm more afraid that everyone, actually I'm not afraid of it, actually be fine. If everyone, aces the thing, then awesome. That means that I did a great job, right? Anyway, so we'll see how it goes. This whole sort of strictly online stuff is sort of, it's new for everyone, so we'll figure it out. I'd rather err on the side of being supportive and giving you more time and making it less stressful than to make it more stressful. So, questions? All right, let's talk about more stuff. All right, so far, everyone's good. The reason I'm laughing is because test-retest, parallel forms, I mean, we can get sort of into the weeds about why, but all that matters is either do the same test twice, correlate it, or 2 different parallel tests and correlate it, and either way is testing for reliability, how consistently they're scoring, with this extra assumption that the reason why people are consistent is because the scores are being driven by the true score sort of behind their measure. Great. Awesome. In reality, nobody wants to do this. Nobody wants to give a test twice. Nobody wants to make two different tests that are supposed to be randomly parallel. It's a lot of extra work just to show reliability of a scale. So if I want to show reliability of scale X, I got to make another one, X prime, just to show that that one's reliable. It seems sort of silly, right? So what do we do instead? Some other alternatives to looking at reliability. Most of these tests that we're talking about, like the CESD, are multiple items that we're adding up to make a composite score. So what if we, instead of making two separate scales, we take one scale that we have with a number of items and we just cut it in half. Use the two halves as parallel forms and see if it's reliable that way. This is what's called a split half reliability. So you have a scale that's 30 items. You randomly just split the test up into two 15-item scales. Like you can go like odds and evens or something. Make two randomly parallel, because that should create two randomly parallel scales that are just half the size. So if we treat halves as one test of parallel forms, so single test is a whole domain, and we just are sampling two different versions out of the same one test, we can do that, and it's called split half reliability. This is testing for internal consistency. So how consistent are the items in this scale at measuring the same thing? So scores on one half of the test should be, you would imagine, correlated with the second half of the test, right? If they're measuring the same thing, they should be consistent. There should be a high level of reliability between the two halves of the test we've created by splitting them up. And the big question is always, well, how do you split them? Some people do literally just take the first 15 and the second 15 and split them up. You can, odd and even. You can create item groups called testlets by sort of randomly selecting and doing the split half multiple times with different randomly combined sort of items to see if you get an average of reliabilities, and that's sort of more mathematically intensive, but you can do that too if you want. Half the time it's like they just split them up between odd and even items, or they'll use some kind of program or something like that to pick the items sort of randomly and create two different randomly parallel halves of the test. Okay. So once you do that, you now have two 15-item tests that you can actually then add up or whatever, the scores. You can give them multiple people, split them up, and create subscale scores, like two different scores, and then we can correlate those. So you're going to split them up, compute scores for two halves of a single test, and then calculate R between the two halves. That's it. All right, so now you just got to give out one test instead of two. You don't have to make a different test. You don't have to do anything. You just got to make one test and then give it to a bunch of people. Split it in half, create sums for the two halves, and then correlate them. But there's a problem there. So it sounds good. Like functionally, it's awesome. I just need to have one test. I can test the reliability all by itself. I don't even need to do any other extra work or create another test. I don't have to make people take the test twice. Right? It solves a lot of problems. But think about domain sampling theory. What's wrong with this? What's wrong with this approach in terms of reliability? What is one of the assumptions that domain sampling theory sort of stated about the number of items on a scale? You don't necessarily cut it in half, but there's a way we can figure that out. But it does cut it, right? So domain sampling theory says, look, you got this, huge population of items, and you're randomly selecting items from the population. But that means that longer tests capture more of the domain, therefore are more reliable. So now we're saying, wait, now we want to take a test that we already created. So we put this whole thing to create this like long 30 or 50 item test. I did all that work to find these items. Now you want to cut it in half, and you're going to completely cut my reliability, not in half, but you're going to cut it back by quite a bit. So a 20-item test cut in half is two 10-item tests, and that's not going to be good for the reliability. The reliability is actually going to be poor. You're actually going to hurt your reliability by, according to domain sampling theory, by using less items. It doesn't make any sense. It's actually going backwards. So, like it says here, if only we could correct for that. Okay. So what we do with split half is we calculate the reliability for split half, and then we use that reliability to figure out what it would be, or what it should be, if we used all 20 items or all the whole test all at one time. So this is what I meant before. This is the Spearman-Brown formula, which you will, there's something you will be tested on, and I think it's in the homework. This estimates the reliability for the entire test based on just the split half. It can actually do more than that. Like, let's say you had 20 items and you were thinking about doubling you wanted to add another 20 items to the same scale. It would also tell you what the reliability would be for the new longer scale. What if you wanted to add in, if you had 20 items, you want to add in 10 more, so that's like half of the original scale. So now you want a test that's 1.5 times the length. You can also figure out what that would be based on this equation as well. So it can also be used to estimate the effect of changing the number of items on a test. So if you want to reduce items or add more items, this equation can tell you what the new reliability would be after you change the number of items. So where R star, R asterisk, is the estimated new reliability. R is the correlation between the halves, or between whatever you have there. And J is the new length. So typically, this will be the reliability we want, because we're doing split half. It's going to be 2 is the new length, twice the number of items, 2 times the split half reliability, plus, over 1 plus the 2 minus 1. So this is typically just going to be 1 times R again. All right, so it ends up being 2 times R plus over 1 plus R, because this ends up just being 1 times R when you add in 2 for J in both places. So anyway, I don't know why I'm just saying that. I can just show it to you. So for split half, we typically will take the 2 halves, correlate them to get the reliability, and then we would use the Spearman-Brown formula to figure out what the reliability is for the full length of the test, twice the split half, by using this equation here. Since the full length of the test is twice the length of each half, that's why we're doing 2 times the split half reliability over 1 plus that same reliability. Will give us our new adjusted correlation. All right, so let's look at it as an example. Let's plug some stuff in. So I have a 30 item test with a split half reliability of 0.65. So my new reliability, okay, the way I'm going to get that is, so it's 0.65, which means it's 30 item test, which means I did 15 and 15 for split half. So I need to do 2 times that 0.65 over 1 plus that 0.65, which is what it said on the previous slide, right? 1 plus 2 times R over 1 plus R, which is the reliability. So what is that? 2 times 0.65 over 1.65. It's like 0.787 or something like that. 0.788. Which, I have 0.79 here. So it doesn't quite get us over that 0.8 hump that we usually want everything to be like 0.8 reliable or more, but it gets us closer. 0.788 is closer to 0.8 than 0.65 is. All right, so if I had a split half reliability for 30 items of 0.65, the reliability of the entire scale would be 0.79 or 0.788. Make sense? Everybody's quiet. Take your silence as go ahead. It's the same equation. It's just the typical the reason why you see this one most often, this version. So think about it. If I wanted to do 2 times, right? I have a split half and I want to double it to see what the full length would be. R star, right on my face. R star would be equal to 2 times R over 1 plus 2 minus 1 times R. This just goes to 1 times R, which ends up being just 1 plus R on the bottom. So it ends up, for 2, it ends up being just 2R over 1 plus R is what it simplifies down if you're just wanting to double it. Now, if I want to triple it, it's not quite that way. R star, let's say I wanted to figure out, I have a 10 item scale and I want to lengthen it to 30 items. I want to triple the amount of items and I want to know, all right, if I did that, what would my reliability be? So I can take the reliability I have for my 10 items and I can figure it out here. I do 3 times R over, it's not going to be 1 plus 3 minus 1 times R, which ends up being 1 plus 2R. The only reason why it simplifies so much with 2 is because this j minus 1, when it's 2s, 2 minus 1 is 1. 1 times R, just R, so it simplifies out. But you could do it for other numbers besides 2. It's just 2 is what we typically use for split half, because we took 30 items, use 15 and 15, so now I want to know what double that would be for 30 items. So that version of it for split half is the one you'll see most often. But they're the same equation, it's just that one simplifies a little bit because of the 2 minus 1. That makes sense? I hope? All right. So let's do another example. This is sort of what I just said, it's sort of the other thing. So I have a 30 item test with a test-retest reliability. So this is now test-retest. This is not split half. I have a test-retest for all 30 items of 0.65. Now I want to know, just out of curiosity, if I were to triple the number of items, I go from 30 items to 90 items, assuming the items stay relatively consistent, that the new items that I add in are equally consistent with the ones I already have, I can then use 3 here, 3 times 0.65, 1 plus 3 minus 1, this ends up being 2. All right, so if I work this out, I get 1.95 over 2.3, and now my 30 item test goes from 0.65 to 90 items with a 0.85 reliability. So think about that for a second. I have 30 items that are 0.65. If I want a scale that goes above the cutoff I want, that 0.8 cutoff, I have to go from 30 to 90 items to get to a level of reliability that actually goes above 0.8. So that's a lot. Now, other way around. What if I'm being told, this happens quite a lot actually. I work with people, they're putting together these large surveys. If you've ever taken a big survey with a lot of different scales and multiple pages of tests, oftentimes they're trying to figure out ways to conserve space, like not to have so many questions. So they have a scale that's 30 items, and they know that scale has a reliability of 0.65, but they want to cut it in half for space, right? So can we pick just the best 15 items or something and use that instead, so we're not asking all 30 items? This actually happens more often than you might think. And oftentimes the researchers don't really think what that means. Well, I swear to God, most of the time they'll think, well, if I have 30 items and the reliability is 0.8, well, we can dump some items and it'll still have the same reliability, which is sort of silly to think, but that's oftentimes the mentality. They don't really think about, well, how's that really going to hurt the reliability? Well, we can figure that out. So if I have 30 items and I want to go down to 15, that means I'm actually cutting, instead of lengthening 3 times like up here, I'm actually cutting it in half. So instead of plugging in 3 here, I can plug in 0.5, that's half the length. So 0.5 times 0.65 plus 1 plus, this is not going to be negative 0.5 times 0.65. Basically 1 minus half of 0.65. You divide those, and now by cutting the test in half, I've dropped the reliability from 0.65 down to 0.48. Right, so this is, again, because of the domain sampling theory, more items are better. Right? So reliability will grow by simply putting more items into a scale. If I cut items out, it's going to hurt the reliability. Okay? Questions? So far, so good? This is all the fun stuff. It's one thing to talk about, like classical test theory in like a theoretical way and blah blah, but actually sort of applying it and actually taking the domain sampling theory ideology and sort of putting it into a mathematical function, to me it's a lot more fun. All right, moving on.